My name is Sebastian Horn. I'm a researcher at the Max Planck Institute for Human Development in Berlin. And in this little video, I'm giving you a short conceptual introduction into the diffusion model. Okay, having a background in experimental psychology, I would like to start with an example that might be an important motivation why to apply diffusion models for data analysis. And this has been termed the metric problem by some researchers. It basically refers to the question how to combine speed and accuracy in typical experimental tasks to assess performance. So imagine the following simple situation. You have three participants that work on a simple, rapid binary decision task. So you have yes and no responses. On each trial, you can now measure the decision time, the latency, and the choice pattern. So you can measure the proportion of correct classifications, for instance. This is a typical phenomenon you often have in experimental psychology, that you have these bivariate responses, these two dependent variables on each trial, consisting of a response time drawn from a continuous positively skewed distribution and a choice, which is binary. However, if we want to assess performance in this task and really know who of the three participants is doing best, this question is not so trivial. So for instance, if we look at latencies, we see that participant A is clearly faster than participant B, but also commits more errors. So only looking at the latencies, we would conclude that participant A is doing better in that task. But looking at the proportion of correct responses, we might come to the opposite conclusion. Importantly, a third possibility would be that the two subjects have exactly the same ability in that task, but simply set different criteria how to weigh speed versus accuracy. So participant A could be willing to make more errors for the sake of being fast. Now let's look at participants B and C. And here we see that the proportion of correct responses is the same, but participant B is by 50 milliseconds faster. So here, most researchers would conclude that participant B's ability is higher in that task. However, it's not trivial to go beyond that ordinal conclusion and really say how much better participant B is actually doing. And this is because speed and accuracy are typically in a nonlinear relationship. So if we plot accuracy, here we see D prime, which is a sensitivity measure of signal detection theory, against response time, we see this clearly nonlinear relationship. So there is this point where accuracy rapidly rises above chance level, and then for each subject reaches a certain asymptote, which means that large changes in response times may be associated with only tiny changes in accuracy. But what we also see is that one and the same decision maker can produce completely different patterns of accuracy depending on when we force him or her to respond. Okay, so this is a general problem that we have when we want to assess performance in such a task. And note that A, B, and C could also be different tasks. And one participant is working on these different tasks, or different groups of participants. So this need not necessarily be three different subjects. One way to address this metric problem are theoretically informed measurement models or process models that account for both dependent variables simultaneously And one such model is the diffusion model. I will not go into the mathematical details in this video. I want to show you the basic conceptual ideas by simply visualizing some core components of the model. So generally, this model assumes that the decision process is influenced by random as well as systematic components. So like in signal detection models, we have a strength of evidence axis, which would be the y-axis in this illustration. However, in extension to signal detection models, we also take into account the variable of time. So information is not only sampled once, but sequentially, repeatedly over time until participants come to a decision. And for this example, let us assume that participants are working on a lexical decision task where you see a letter string and simply have to decide whether it is a word or a non-word. The model assumes that information accumulation starts at a point z that lies somewhere between two decision thresholds, in that case for words and for non-words. So the assumption is that when a stimulus is shown, information is sampled sequentially until one of the thresholds is crossed and then the corresponding decision is made. Note that due to random influence in this model, decision processes do not always terminate at the same time. So there's a lot of variability in this accumulation process, and also do not necessarily terminate at the same threshold, thereby producing errors. So this implies that the model predicts across trials decision time distributions associated with the upper and the lower threshold. Importantly, however, there's a systematic component driving the decision, which is captured by the drift rate parameter. The direction and the slope of that parameter determines how much information is accumulated in favor of a particular decision per time unit. So you can interpret this as the speed of information accumulation or processing efficiency. So all other things being equal, higher drift rate, as shown here in the red condition, implies that decisions are faster. So the decision time distributions get less skewed and also more accurate. So you will have, in this example, you will have more accurate decisions, will have more processes terminating at the upper threshold in this example. In that way, we can measure participant ability or task difficulty, the information provided by a stimulus, with this parameter. There is another important parameter in this model, namely boundary separation, the distance between the two thresholds, which captures a decision maker's speed accuracy criterion. So if boundary separation is reduced, what happens is that on average, calculation processes will reach one of the thresholds more quickly. So we will have faster decisions, but these decisions will also be less accurate because the relative impact